Now we're going to look at some examples of normal subgroups using one of the definitions of left cosets are equal to right cosets. So the definition of a normal subgroup is the following. H is a normal subgroup of G if, for every element in the group, larger group G, and every element in the subgroup H, this triple product is an element in H. I will refer to this by saying the conjugate of H by G is in H, because that is the phrase we use to refer to this triple product. And you've actually seen this triple product before in linear algebra classes in the context of matrices. At the very least in, say, diagonalization. A matrix is diagonal or diagonalizable if it is a conjugate of a diagonal matrix. And it's invertible if it's a conjugate of an identity matrix. Or no, not quite. But usually there's this thing called being similar. Matrices are similar if one is the conjugate of another. And so this same notion can be generalized to group theory. And there we actually use the word conjugate instead of similar. But here it is. I say theorem and not just definition because for me, this is the definition of being a normal subgroup. However, if you read the textbook, this is the textbook's definition. And one of the theorems in the textbook is that these three statements are equivalent. So, as a theorem, these three statements are also equivalent. And so when you have three equivalent statements, any one of them can be chosen to be the definition if you want. So I'm going to continue to refer to this as the definition, but all three of these statements, if one of them is true, all three of them are true, and if one of them is false, all three are false. And we will prove this equivalence in a later video. For this video, we will look at examples of subgroups and ask ourselves, is it normal? And mainly we'll be doing that to see how these conditions can be used. You'll see for small concrete examples, this last definition is actually the most useful, which is why the textbook chooses it as its first definition. I never actually understood that as a student, because when you look at abstract examples for the purposes of proofs, the first definition is actually better. Also note this second definition says that these two sets are equal, but the textbook almost never defines what this set is. This set is the set of conjugates. So it says the set of conjugates is equal to H. And the third condition just says for every group element, the left coset with respect to that element is equal to the right coset with respect to that element. So here's the first example. Let G be S3. Let H be this subgroup. G mod H by Lagrange's theorem, the number of cosets is the size of G divided by the size of H. 6 divided by 2 is 3. We already did this example in a previous video and wrote down all three cosets. I didn't actually write down the third coset this time, because the question we're asking is H normal in G? Turns out you don't need to know all the cosets to figure that out, because the third condition says the left coset must be equal to the right coset. And so once you write this one down, you can check that this is false. And that was a homework exercise. So in this case, the answer is no. H is not a normal subgroup in G. Next, let's take the symmetric group again, but now we'll take the subgroup H to be the 3-cycle. Now there's only two cosets. Well, what do we need to check? we need to check if the left coset with respect to 1, 2 is equal to the right coset. This turns out to be a little easy to show because, well, both these cosets have the same size, and both of them have to be contained in the symmetric group. Take away this subgroup, which has size 3, and so in fact both these cosets is equal to S3 take away H, which means they're equal to each other. So that one's trivial. And that actually gives you an idea that whenever H has index 2, then H is normal. It's exactly this idea, because the left coset and right coset are the only non-trivial coset. The left and right are both equal to the set difference G take away H. So of course I should say yes, H is normal in G. A normal subgroup of G. So the next example, much bigger, we'll let G be A4 with that has 12 permutations. We'll let H be this particular subgroup of 4 permutations. By Lagrange's theorem, the number of cosets is 3. So we got to find the 3 cosets here. So recall A4, it contains these 4 elements in H, and it also contains all these 8 cycles, all 3 of them. And so one choice of cosets ends up being 1, 2, 3, and its inverse. 1, 2, 3 inverse, 1, 3, 2. That actually turns out to work quite well. And so we want to know, is H normal in A4? Well, we actually have to do this sanity check. Is this left coset equal to this right coset? Well, let's compute this left coset. Here I am multiplying by the 3 permutations in H. By 1, 2, 3. Here are the 4 3 cycles appearing in this coset. Notice the pattern here, by the way, and this is why I underline them in advance. The 4 elements in this coset give you 4 of the 3 cycles. All their inverses are, for each of these underlined 3 cycles, their inverse is not underlined. So their 4 inverses end up in the other coset. That doesn't help with the proof much, but it is kind of interesting that that structure happens. Now we, of course, compute the right coset. Now I'm multiplying each of these permutations in H on the right by the permutation 1, 2, 3. I get these 4 3 cycles. I check that I got 1, 3, 4. I got 1, 4, 2. And I got 2, 4, 3. So these 2 cosets are in fact equal. Again, it turns out these 2, there's only 1 coset left to check. You have to check that these 2 cosets are also equal. However, we remember that the cosets partition G, and so this coset is the remaining 4 elements, which means those remaining 4 3 cycles that have not appeared yet. And this coset, the right coset's also partition G, and so this set is also the remaining 4 cycles, 3 cycles that have not appeared. It's the same for 3 cycles. So these are the same sets. So we don't have to do any calculations. Logic and our knowledge of cosets already tells us these two have to be equal. This brings up a very common misconception. About normal subgroups. We see that this is true, but it's not the case that we have this type of commutativity. So the left coset's equal to the right coset, but that doesn't mean multiplying elements of little h times elements of little g commute. What this says is that when you have little g times little h, then you're going to be able to get little g times little h prime. And the best example you see is right here. We see right off the bat that 1, 2, 3 times 1, 2, 3, 4 is definitely not equal to 1, 2, 3, 4 times 1, 2, 3. Those are different permutations. What is true is that 1, 2, 3, 4 times 1, 2, 3 is equal to, if I move the 1, 2, 3 on the other side, I'm going to get 1, 4, 2, 3. So you're replacing this element in your normal subgroup with a different element in the normal subgroup. So it's sort of like a commutativity, but the element in the subgroup is getting replaced. So that's an important trap not to fall for. So it's sort of a generalization of commutativity, but it's slightly different.